Alright, hey there. I'm going to show you how to solve for the distance that a ball will travel, given a initial velocity at an angle of theta from the ground. You could imagine a baseball player hitting a ball with a specific launch angle, that would be v, or a launch angle which would be theta, and an exit velocity of v. Now, the first thing we need to do is figure out how long the ball is in the air. And in order to do this, we can see how long it will take the ball to fall from its maximum height. And so the formula for that is going to be height is equal to 1/2 acceleration times time squared. Now, we don't know the height and we don't know the time, but we're trying to solve for time. And so we're going to rearrange this formula to be t is equal to the square root of g, which is our acceleration, over 2h. Now, to calculate h, we can use a conservation of energy. The initial energy is going to be all kinematic energy, which is, so E initial equals E final. The initial energy is 1/2 mv squared. Now this is going to be the y component of our velocity, and I'll get to that in a second. And this is going to be equal to gravitational potential energy, which is mgh. Now remember, velocity is a vector, so it has a y component and an x component. This will be helpful later on. Now, in order to solve for h, we see that the masses cancel out, and we get that h is equal to vy squared over 2g. Oh, I'm sorry, this is incorrect. This should be square root of h over 2g. Now we input this h into our formula here, and we get time is equal to the square root of 1 over 2g times vy squared over 2g. And remember that we need to multiply this time by 2 because we're seeing how long it takes the ball to fall from height h. And so we also need to take into account the time it takes to go up to height h, which will be the exact same as the time it takes to fall because the acceleration from gravity is constant. Now, after doing some cancellation, we get that this is equal to vy over g. Nice. So now we have the amount of time. We just see how far that ball will travel in that amount of time. And we know the x component of the velocity. And so we know that distance is equal to vx times time, which, since we know the time, is equal to vx times vy over g. Now, in order to get this in terms of the initial velocity, we need to do some trigonometry. So vy, vx, and using some geometry, we get that vy is equal to v sine theta, and vx is equal to v cosine theta. Now doing some simple substitution, we will get our final formula for D, which is V squared sine theta cosine theta over G. And this is our final answer. Now this makes sense because you'd expect with a higher velocity, the ball will go farther. So as V goes up, D goes up. If there's more gravity, we'd expect it to go a shorter distance. And if there's less gravity, we'd expect it to go farther. So as gravity goes down, distance also goes up. And the optimal angle is going to be 45 degrees, which will give you a higher distance. So as theta approaches 45 degrees, D goes up. All this checks out, and that is why this is our answer. Now this is a pretty straightforward projectile motion problem here. You'll see it a lot in intro-level physics, and you can tweak some of the variables, but if you follow this formula, you should be able to handle anything your teacher throws at you. So thank you. Let me know if you have any more suggestions for videos.